Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
The record begins far from the Sun, where the solar system thins into a region defined more by motion than by structure. Here gravity weakens and the influence of individual planets fades into a combined pull that shapes long, slow arcs. Objects arriving from this distance do not announce themselves with spectacle. They enter quietly, carrying velocity set long before they cross the boundary where surveys can detect them. The object designated 3I Atlas is first recognized in this outer context, not as a body with properties, but as a trajectory that does not belong. Its path does not curve as a bound orbit would. Instead, it traces a line that arrives from interstellar space, passes through the planetary plane, and continues onward. This alone is sufficient to mark it as different from the countless asteroids and comets native to the solar system. The distinction is geometric before it is physical, a matter of where the path leads when traced backward beyond the Sun's influence. In this outer region, explanation remains minimal. The role is to register motion to note that the object approaches on a hyperbolic course, one that cannot be reconciled with long-term residence here. The environment at this scale is sparse. Dust densities are low. Radiation from the Sun is present but weak. The object's surface temperature changes slowly, governed by distance rather than activity. Nothing about this region imposes complexity. Forces act smoothly and predictably. Against this calm background, the arrival of an interstellar object is not disruptive but rare. Rarity draws attention, yet attention must remain disciplined. The first task is confirmation. Multiple observations are required to rule out error. Positions are measured against starfield's timestamps. Compared uncertainties reduced. As data accumulates, the path remains consistent. The object is real and it is inbound. At this stage, nothing more is required. There is no need to speculate about composition or behavior. The outer region allows only one statement. Something from beyond the solar system is passing through. The designation reflects this. The leading numeral marks it as the third such object identified. The remainder of the name ties it to the survey that first reported it. Names carry no implication beyond record keeping. They do not describe nature. In the outer region, the object is still distant, its light faint and unresolved. Telescopes collect photons that have travelled for hours across space, reflected from a surface that remains indistinct. Brightness is measured, but brightness alone is ambiguous. A small reflective body and a larger dark one can produce similar signals. Distance estimates reduce some uncertainty, but much remains. The outer region tolerates this. Precision increases only gradually as the object approaches. The solar system at this scale functions as a detector with long integration times. Motion reveals itself more readily than matter. The object's speed relative to the Sun is high, consistent with an origin not bound by solar gravity. This speed does not change abruptly. It follows expectations derived from celestial mechanics. There is no sign yet of deviation. The object behaves as any mass would under gravity alone. This is important. Early behavior establishes baseline. Without baseline, later interpretation drifts. Section 1 remains anchored here where nothing unusual has occurred beyond arrival itself. Interstellar objects are uncommon but not forbidden. Galactic dynamics predict their existence. Stars form with surrounding material. Some of that material is ejected during planetary formation or later through gravitational interactions. Over billions of years, these fragments populate interstellar space. Most never encounter another star closely enough to be noticed. A few pass through regions where detection is possible. 3I Atlas is one of these. Its detection reflects the sensitivity of modern surveys as much as the object's properties. The outer region is defined by this interplay between vastness and selectivity. Many objects pass unseen. This one does not. Detection does not imply significance beyond that fact. It implies alignment between motion and instrument capability. As observations continue, the orbit is refined. Errors shrink. The hyperbolic nature becomes secure. The inbound direction is mapped relative to the galactic frame, though uncertainties remain large. At this distance, small angular errors correspond to large spatial differences. Origin cannot be traced to a specific star. The role is to state this limitation plainly. The outer region does not permit stories of origin. It permits only vectors and probabilities. The object's inbound path suggests a long journey through interstellar space exposed to cosmic radiation and low-density environments. This exposure is noted but not elaborated. Without proximity, its effects cannot be measured. The object remains a point of light moving against a fixed background. There is no coma, no tail, no visible activity. This absence is not yet meaningful. At large distances, even active comets appear inert. Temperature is too low for volatile release. The sun's influence has not intensified enough to provoke change. Section 1 stays with this restraint. Nothing is implied by silence. As the object continues inward, the solar system begins to exert more influence. Gravitational acceleration increases. The path curves slightly as expected. This curvature is predictable. Models reproduce it easily. Residuals are small. There is no reason to introduce additional forces. The object's brightness increases gradually as distance decreases. This follows the inverse square relationship between light and distance modified by phase angle. These are routine considerations. The outer region is governed by routine physics. This routine is essential. It establishes trust in measurement and model alike. Without it, later deviations could not be identified as such. Section 1 therefore remains deliberately uneventful. It describes an object entering a system obeying known laws, revealing only that it comes from elsewhere. The significance lies not in behavior but in classification. Interstellar origin is confirmed. Everything else is deferred. The outer region has been fully traversed. The object has been placed within the solar system's frame of reference without alteration to that frame. Nothing has been added, nothing inferred beyond what motion requires. This is where the account must pause before moving inward. As the object moves further inward, its trajectory begins to intersect regions where the solar system's internal order becomes clearer. Planetary orbits define lanes of motion shaped by long residence and repeated interaction. Most small bodies here follow paths that reflect this history. Their inclinations cluster near a plane, their velocities constrained by prior capture. 3I Atlas does not conform. Its path cuts through these established patterns at an angle that immediately distinguishes it from resident populations. This distinction is not dramatic, but it is persistent. Each new observation reinforces the same conclusion the object is passing through rather than belonging. The role at this stage is to refine that conclusion with precision, translating positional measurements into a coherent orbital solution. Astrometric data accumulates over successive nights. Each position is measured relative to background stars whose own motions are well characterized. Corrections are applied for Earth's rotation and orbit for light travel time for atmospheric effects. These corrections are routine yet essential. Without them, apparent deviations could masquerade as physical behavior. Once applied, the remaining motion of 3i Atlas aligns cleanly with a hyperbolic orbit. Its eccentricity exceeds unity by a margin that grows more secure as uncertainties shrink. This margin matters. It marks the boundary between bound and unbound motion. Crossing it places the object firmly outside the solar system's long-term inventory. In this inner context, gravity's influence increases, but it remains orderly. The Sun dominates with planets contributing secondary perturbations. These perturbations are calculable. Their effects on the object's path are small but measurable, especially as it approaches the region near the planetary plane. Models incorporate these influences, producing predictions that can be tested against observation. At this point, the match is close. Residuals remain within expected ranges. There is no indication yet that additional forces are required. The object's velocity relative to the Sun is high, but consistent with interstellar passage. It does not decelerate into capture. It does not accelerate beyond gravitational expectation. The path is smooth. This smoothness is important. It sets expectations for later comparison. Brightness continues to increase as distance decreases. Telescopes with greater sensitivity now contribute data extending coverage across wavelengths. Photometric measurements indicate a surface that reflects light, without obvious variation over short timescales. There are no sudden flares, no asymmetries suggestive of jets. The object remains unresolved, its angular size too small for direct imaging. Shape must be inferred indirectly if at all. In the inner region now being traversed, temperature rises gradually. Models estimate surface heating based on distance and assumed thermal properties. These estimates remain coarse. Without knowing composition or structure, temperature is a range rather than a value. Still, the range places the object below thresholds where common ices would sublimate vigorously. The absence of a visible coma remains unremarkable. Many comets remain inactive until closer approach. Section 2 maintains this restraint. It does not elevate absence into anomaly. The path continues to be the primary focus. As more data arrives, the inbound direction is refined. The object approaches from a region of the sky that does not correspond to any known stellar association with high confidence. This is expected. Interstellar travel over long durations erases clear links to origin. Small gravitational nudges accumulate. Galactic tides act slowly. Encounters with other stars, even distant ones, alter trajectories. By the time an object reaches another system, its path encodes only broad statistical information. Section 2 stays within this statistical frame. It avoids naming stars or regions as sources. The role is to state what can be constrained and leave the rest open. Within the solar system, the object's path brings it closer to regions of denser observation. Survey cadence increases. Positional accuracy improves. The orbit solution stabilizes. At this stage, analysts examine residuals carefully, not because they expect surprise, but because this is the moment when subtle effects would first become detectable. Residuals show small scatter consistent with noise. No systematic trend stands out. The conclusion remains that gravity alone accounts for observed motion. This conclusion is provisional, but it is sufficient for now. Section 2 emphasizes that provisional sufficiency is not weakness. It is the default state of early characterization. The object's designation remains unchanged. No special flags are attached. It is catalogued as interstellar monitored and allowed to proceed. The solar system does not react to its passage. Planets continue their orbits. Background objects remain fixed relative to one another. The event is observational, not dynamical. As the object moves deeper inward, the Sun's influence begins to dominate its energy budget. Radiation increases, the surface warms. Thermal models predict gradual changes in reflectivity as phase angle shifts. Observed brightness tracks these predictions within uncertainty. This agreement reinforces confidence in baseline assumptions. Section 2 lingers on this agreement because it forms the reference against which later divergence will be measured. Without a clear baseline, later interpretation would be untethered. The narrative therefore remains methodical. No language of surprise is introduced. The object is doing what objects do when they fall inward under gravity and reflect sunlight. The inner boundary of this section approaches as the object nears distances where activity, if present, would begin to manifest. This boundary is defined not by speculation but by physics. Certain materials change state above certain temperatures. Certain forces become comparable in magnitude only within certain ranges. Section 2 stops just short of these thresholds. It closes with the object firmly inside the solar system's observational envelope, its path well defined, its behaviour unremarkable by current measures. Everything that follows will depend on how it behaves once additional forces beyond gravity and passive reflection become relevant. For now, none are required. The role remains intact. Description precedes interpretation. Motion precedes meaning. The trajectory of 3i Atlas, traced carefully and without embellishment, continues inward along a path that is unusual only in origin, not yet in behaviour. As 3i Atlas advances further inward, observations shift from confirmation to characterization. The object now occupies a region where changes, if they occur, can be detected with increasing confidence. This is the zone where expectations begin to form not because of novelty, but because physics predicts transitions. Sunlight grows stronger. Thermal gradients across the surface increase. Materials that were inert at greater distances approach conditions where they may respond. The role at this stage is to watch carefully without assuming response must occur. Many small bodies remain quiet even under moderate heating depending on composition and structure. Early measurements are therefore treated as probes rather than signals. Photometry becomes more precise as brightness improves. Light curves are constructed by tracking changes in reflected light over time. These curves are initially flat within uncertainty, suggesting either slow rotation or a shape that presents little variation in cross-section. Neither conclusion is firm. Noise remains comparable to signal. Analysts refrain from fitting rotation models prematurely. The object is still too distant for confident inference. Astrometry continues in parallel, refining position and velocity. Gravitational models remain adequate. Residuals are recalculated with each new dataset and they remain small. This persistence matters. It establishes that up to this point the object behaves exactly as a passive body should. Any later deviation will therefore stand out clearly against a well-defined history. Spectral observations are attempted as instrumentation allows. The returned spectra are low resolution, limited by faintness and motion. They show a generally neutral to slightly reddish slope, consistent with many small bodies exposed to cosmic radiation over long periods. Such slopes are common among outer solar system objects and among previously observed interstellar visitors. They imply surface processing, not composition specificity. No strong absorption features emerge. The absence of features does not imply absence of material. It reflects the limits of signal quality. Section 3 remains explicit about this distinction. Non-detection is not negative evidence when sensitivity is insufficient. The object's environment continues to simplify interpretation. At these distances, the solar wind is present but diffuse. Its interaction with neutral surfaces is weak. Radiation pressure exerts force, but at this scale, its contribution to motion remains negligible, compared to gravity for objects of typical density and size. No attempt is made yet to quantify such effects. Doing so would introduce assumptions not yet justified. The role demands patience. As the object approaches the region wherein a planet's orbit observational cadence increases, surveys hand off to targeted follow-up. This transition reflects confidence in identification, not concern. The object has earned attention by persistence, not by anomaly. Data quality improves accordingly. Position measurements tighten. Photometric uncertainties shrink. With this improvement comes the first hint of variability in brightness. The variation is subtle, barely exceeding noise, but it repeats over multiple observation windows. Analysts note it cautiously. Repetition distinguishes signal from fluctuation. The amplitude is small, suggesting either a modest elongation or a rotation axis oriented such that cross-section remains nearly constant from Earth's perspective. Both are plausible. No further inference is drawn. Section 3 emphasizes that early hints are treated as placeholders, not conclusions. The object continues inward, and with it the sun's influence grows. Surface temperatures approach ranges where common ices such as water would begin to sublimate if present near the surface, yet no coma appears. Imaging shows a point source consistent with a bare nucleus. This absence begins to register not as anomaly, but as constraint. If volatiles exist, they are either buried, depleted, or released in a manner not easily detected. Each possibility is noted without preference. Section 3 carefully avoids ranking explanations prematurely. The absence of a tail or coma also simplifies astrometric analysis. Coma can shift the apparent center of light relative to center of mass introducing biases. Without it, positional measurements more directly reflect the object's true motion. This clarity reinforces confidence in orbital solutions. Analysts take advantage of this by recalculating fits with higher order terms, disabled testing whether gravity alone remains sufficient. For now, it does. The object's acceleration matches prediction within margins. Any deviations are below detection thresholds. This result is recorded and retained as baseline. The object's path relative to planets is also examined. It passes at distances that produce minimal perturbation. No close encounters occur that would complicate interpretation. This isolation is helpful. It means that any future deviation cannot be attributed to recent planetary interaction. Section 3 notes this explicitly as it will later matter. Rotation analysis is revisited as more photometric data accumulates. A tentative periodicity emerges, but it remains uncertain. The data supports multiple solutions. Analysts refrain from choosing among them. Instead, they report ranges. This restraint reflects the role's priority accuracy over completeness. In the inner solar system, many objects exhibit increased activity as they warm. 3i Atlas does not. Its brightness continues to follow a smooth trend dominated by distance and phase angle. This smoothness is now noted as characteristic. It distinguishes the object from active comets, but aligns it with inert asteroids. Yet its interstellar origin complicates this comparison. Asteroids are typically rocky and dense. Interstellar objects may not share this composition. Section 3 holds this ambiguity. It does not collapse categories. The object remains interstellar first, inert second, with the relationship between these labels unresolved. As the object draws closer to the Sun, observation windows lengthen. Longer integrations improve signal quality. Spectral slopes are refined. They remain consistent with processed surfaces. No new features appear. This consistency reinforces the impression of a surface that has been exposed to interstellar conditions for extended periods. Cosmic rays, micrometeoroid impacts, and ultraviolet radiation alter surfaces, slowly darkening and reddening them. Such effects are well documented. Section 3 invokes them only to explain plausibility, not to assert history. The object's history remains inaccessible. Only its present state is described. At the inner boundary of this section, the object approaches distances where subtle forces may begin to compete with gravity in measurable ways. Radiation pressure increases with proximity to the Sun. Thermal processes intensify. If any non-gravitational acceleration exists, it will soon become detectable against the established baseline. Section 3 ends deliberately here, with the object poised at a threshold defined by physics, not narrative. Everything observed so far fits within ordinary expectation for a passive interstellar body. That ordinariness is now well documented. The record is clean. The role has been maintained. What comes next will be evaluated against this record without reinterpretation of what has already been measured. He turns now from light to movement, from what 3I/Atlas looks like to how it travels. Motion is usually the most obedient language in astronomy. Objects fall, orbit, drift, accelerate, and slow, according to equations refined over centuries. Even when the universe surprises, it does so within boundaries that can be tested, modelled, and eventually named. But here in the quiet calculation surrounding 3I/Atlas motion begins to feel unsettled, as if the object is answering a question no one thought to ask. At first glance, its trajectory seems unremarkable. It is not on a closed orbit around the Sun. It is not bound to any star. Its path curves through the solar system and continues outward, a visitor passing through rather than a resident settling in. Such paths are rare but not unprecedented. Interstellar objects are expected to move fast, arriving from distant origins with velocities that reflect the gravitational history of other star systems. In that sense, 3I/Atlas behaves as expected. It comes in quickly, it leaves quickly. This Sun bends its path but does not capture it. Yet when astronomers refine the measurements, when they subtract known gravitational influences and account for observational uncertainty, a residue remains. A small discrepancy, a gentle but persistent deviation between predicted motion and observed position. It is not dramatic. It does not announce itself with sudden turns or impossible speeds. It whispers instead, appearing only after many nights of careful tracking, after error bars have been tightened and recalculated. This is the moment where experience becomes caution. Astronomers know that apparent anomalies often dissolve under scrutiny. Instrumental bias data gaps, background noise, unmodelled forces, these are common culprits. So the first response is restraint. The models are checked. The timestamps are verified. Independent observatories compare notes. Nothing obvious is wrong. The deviation remains small, but it remains real. Non-gravitational acceleration is not unknown. Comets experience it regularly. As they approach the Sun, volatile ices sublimate, releasing jets of gas that act like tiny thrusters. Over time, these jets can measurably alter a comet's trajectory. The effect has a signature. It increases with solar heating, aligns with the object's orientation, and often coincides with visible activity such as comas or tails. So astronomers look again at 3I/Atlas. They search for signs of outgassing. They stack images, stretching contrast, hunting for diffuse halos or asymmetric light. The object remains stubbornly compact. No tail unfurls, no coma blooms. Its brightness changes, but not in a way that clearly signals active jets. If gas is escaping, it is doing so quietly, invisibly, or in quantities far smaller than expected. This is where the unease begins. Because motion without a clear cause is not merely a puzzle, it is a challenge to classification. If 3I/Atlas is comet-like, its behavior should advertise that fact. If it is asteroid-like, its motion should be almost purely gravitational. Instead, it occupies a narrow and uncomfortable middle ground, borrowing a trait from comets without wearing their visible signs. The calculations grow more refined. Solar radiation pressure is considered. Photons, though massless, carry momentum, and for very small or very low density objects, sunlight itself can exert a measurable push. This effect has been proposed before, sometimes controversially, as an explanation for unexpected accelerations. The math is straightforward, but the implications are not. For radiation pressure to matter at this scale, the object must have an unusually high area-to-mass ratio, thin, fluffy, or shaped in a way that maximizes exposure to light. Does 3I/Atlas meet these criteria? The data do not offer a clear answer. Its brightness suggests a certain size, but brightness depends on reflectivity, shape, and orientation. A dark object can be large and still appear faint. A reflective one can masquerade as smaller than it truly is. Rotation complicates everything, changing how light is scattered over time. The uncertainty remains wide enough to admit possibilities that feel to some uncomfortably exotic. Still, restraint holds. No extraordinary claims are made. Instead, the focus remains on what can be said with confidence. The acceleration is small. It does not violate physics. It does not demand new forces or new laws. But it does ask for a combination of properties that is uncommon. And uncommon in astronomy is often where discovery begins. He lingers on the idea of origin. If 3I/Atlas formed around another star, its composition reflects conditions not found here. Different temperature gradients, different chemical abundances, different histories of collision and radiation. What seems strange in the solar system may be ordinary elsewhere. Perhaps materials that sublimate invisibly to our instruments are common around other suns. Perhaps structures that respond subtly to light pressure are more frequent than we imagine, simply underrepresented in our local neighborhood. The object's speed offers another clue. Interstellar visitors carry the kinematic memory of their birthplaces. Their velocities relative to the Sun are shaped by galactic tides, stellar encounters, and the slow churn of the Milky Way. 3I/Atlas does not arrive with an extreme velocity. It is fast, but not impossibly so. This suggests it was not violently ejected from a catastrophic event, but rather gently nudged over time, drifting free from its parent system after eons of quiet perturbation. Such a history favors fragility. Objects that survive explosive ejection tend to be dense and robust. Objects that drift away slowly can be porous, loosely bound, even delicate. This again fits with the idea of subtle, non-gravitational effects. A fragile structure responds to forces that a solid rock would ignore. As nights pass and data accumulates, the deviation becomes a feature rather than a flaw. It is folded into the models not as an embarrassment, but as a parameter to explore. Different assumptions produce different futures for the object's path, but all agree on the broad outline it will pass through, and it will leave carrying its unanswered questions with it. There is a quiet tension here, one that does not resolve easily. Motion is supposed to clarify. It is supposed to reduce ambiguity, not deepen it. Yet in this case, movement becomes another layer of mystery, another axis along which 3I/Atlas resists simple explanation. He reflects on how often astronomy advances this way, not through spectacle but through discomfort, a decimal point that will not settle, a residual that refuses to vanish. These are the seeds from which entire fields grow. The discovery of Neptune began as a discrepancy in Uranus's orbit. The expansion of the universe emerged from faint redshifts that did not fit expectation. In each case, motion spoke softly before it spoke loudly. For now, 3I/Atlas speaks softly. Its path curves just enough to be noticed. Its speed changes just enough to be measured. Nothing about it shouts. And yet within that restraint there is insistence, a reminder that the universe does not owe us neat categories. As the section closes, he allows the motion to fade into the background like a heartbeat felt more than heard. The object continues on its way, obeying gravity, light, and its own internal nature, whatever that may be. Astronomers continue to watch, to measure, to recalculate. And somewhere between prediction and observation, a narrow space remains open, a space where explanation has not yet arrived, and curiosity is allowed to breathe. He turns now from how 3I/Atlas moves to the more delicate and more dangerous question of what it actually is. Classification is the quiet backbone of astronomy. To name an object correctly is to place it within a network of expectations, how it formed, how it evolves, how it dies. Stars, planets, asteroids, comets, each name carries with it an inheritance of physics. But every so often an object arrives that seems to hover between labels, borrowing traits without fully accepting any single identity. 3I/Atlas occupies precisely this uncertain space. At first the language comes easily. It is small. It is not self-luminous. It reflects sunlight. These traits place it among minor bodies far from the grandeur of stars or planets. Its unbound trajectory marks it as interstellar, a visitor rather than a native. So far the taxonomy holds. But beyond these basics, clarity dissolves. If it were a comet, astronomers would expect certain behaviors. Volatile ices preserved from formation in cold outer regions should awaken as the object approaches the sun. Gas should escape, dust should lift, and sunlight scattering through that material should create a visible coma or tail. Even weak comets usually betray themselves eventually. Yet 3I/Atlas remains visually restrained. Its light profile stays compact. Its edges do not soften into a diffuse cloud. It refuses the classic cometary display. If it were an asteroid, a different set of expectations applies. Asteroids are typically inert, rocky, or metallic bodies whose motion is governed almost entirely by gravity. They do not accelerate mysteriously. They do not shed mass in ways that alter their paths. And yet, as already seen, the motion of 3I/Atlas does not fit comfortably within this inert picture. Something is acting upon it, something subtle but persistent. So astronomers begin to reach for hybrid language. Dormant comet, extinct comet, transitional object. These phrases acknowledge uncertainty while preserving known categories. A comet may exhaust its surface volatiles over time, leaving behind a crust that suppresses visible activity. Beneath that crust, however, ices can remain, releasing gas in slow, uneven ways. Such objects exist within our solar system. They blur the line between comet and asteroid, but even this explanation strains under scrutiny. Most known dormant comets still show occasional outbursts or faint comas when observed carefully. Their histories are usually traceable. They belong to populations shaped by the Sun over millions of years. 3I/Atlas, by contrast, has no solar history. Its surface has not been baked and reworked by repeated close passages. If it is dormant, it must have become so elsewhere, under conditions not yet well understood. Attention shifts then to composition. What materials could drive non-gravitational motion without producing obvious visual signatures? Some candidates are familiar. Carbon monoxide and carbon dioxide can sublimate at lower temperatures than water ice, and can do so more gently, producing less dust. Hydrogen, the lightest element, can escape almost invisibly, carrying momentum without much optical consequence. There are even more exotic possibilities: amorphous ice, crystallizing, internally releasing trapped gases in small amounts, or porous matrices that leak volatiles diffusely rather than explosively. Each proposal is physically plausible. None can be confirmed directly. The object is too small, too distant, and too fleeting for detailed spectroscopy that would decisively reveal its makeup. Instead, astronomers infer composition indirectly, reading behavior the way one reads a shadow to guess the shape of an unseen object. There is also the matter of shape. Shape influences everything: brightness variations, response to radiation pressure, thermal behavior, and gas release patterns. A spherical body behaves predictably. An elongated or irregular one does not. If 3I/Atlas is highly asymmetric, it could experience uneven heating as it rotates, driving localized outgassing that never builds into a global coma. Light curves offer hints but not certainty. The data suggest rotation, but the exact form remains elusive. He pauses on the deeper implication: classification itself may be the wrong question. Perhaps 3I/Atlas is not strange because it violates our categories, but because our categories are provincial. They are built from a single planetary system observed from the inside. Interstellar objects by definition sample a much larger range of formation environments. What appears hybrid here may be commonplace elsewhere. In this view, comets and asteroids are not distinct species, but points along a spectrum of small body evolution. Composition, structure, and activity vary continuously, shaped by local conditions rather than strict archetypes. 3I/Atlas may simply occupy a region of that spectrum rarely represented in our immediate cosmic neighborhood. This idea is both comforting and unsettling. Comforting because it preserves known physics. Unsettling because it implies that much of what we think we know is incomplete, skewed by observational bias. We have built our understanding from what remains bound to the Sun, from survivors shaped by its influence. Interstellar visitors are different by definition. They are the emigrants, the escapees, the objects that did not stay. As debate continues, language becomes careful. Papers avoid definitive nouns. They favour phrases like consistent with and suggestive of. Conferences host quiet disagreements, not over data but over interpretation. Some researchers lean toward commentary explanations, arguing that invisibility does not imply absence. Others emphasize radiation pressure and unusual structure, pointing to the object's response to light rather than heat. No one claims certainty, and no one rushes to conclusions that would demand extraordinary explanations. The memory of past controversies lingers. Astronomy has learned, sometimes painfully, the cost of overreach. It proceeds now with humility, allowing ambiguity to persist. Yet the ambiguity itself is productive. It forces new models, new simulations, new laboratory experiments. Materials scientists recreate porous ices under vacuum. Dynamicists explore how irregular shapes interact with sunlight. Chemists revisit phase transitions that might occur in interstellar conditions. Even without a final answer, 3, I/Atlas is already reshaping inquiry. He reflects on how rare this moment is. Most objects are understood by the time they're named. Here the name arrives first and understanding trails behind. The designation 3I marks it as the third known interstellar object, a category that barely existed before this century. Each addition to that list carries disproportionate weight. With so few examples, every anomaly feels amplified, every uncertainty significant. As 3I/Atlas recedes from the sun, opportunities narrow. Its activity, whatever its nature, will diminish with distance. Its brightness will fade into the background of stars. Eventually it will slip beyond the reach of even the largest telescopes. Classification may remain unresolved, a footnote marked with question marks. And yet even an unresolved question can be valuable. It sharpens the boundaries of knowledge by revealing where those boundaries fail. 3. I/Atlas may never be cleanly labelled, but in resisting labels it teaches caution. It reminds astronomers that nature does not organise itself for human convenience. The section closes not with an answer but with a reframing. Perhaps the most honest description of 3I/Atlas is not a noun at all but a role. It is a messenger, a fragment of another system carrying within it the imprint of processes that unfolded far from here. Its refusal to fit neatly into our schemes is not a flaw in observation, but a signal, a quiet indication that the universe is broader, more varied and more inventive than our categories can yet contain. He turns deliberately to method because method is where uncertainty is made manageable. When an object behaves in a way that draws attention, the response is not imagination but procedure. The history of astronomy has trained this reflex carefully. Before anything unusual is claimed, every ordinary explanation must be tested, adjusted and tested again. With 3I/Atlas, this process unfolds quietly, and in parallel across institutions, each group working with the same data, but approaching it from slightly different angles. The first step is gravitational accounting. The object's path is reconstructed using precise astrometry, with corrections applied for the gravitational influence of the Sun, the major planets, and even relativistic effects where necessary. These calculations are routine refined over decades of planetary science. The question is simple: does gravity alone explain the motion? For most bodies, the answer settles quickly. Here residuals remain. They are small but persistent, and they do not disappear with improved fits. The trajectory bends just enough to demand something more. Non-gravitational forces are not exotic in themselves. Comets have long been known to deviate from purely gravitational paths as gas escapes their surfaces. The recoil from outgassing acts like a gentle thruster, altering velocity over time. Standard models describe this behavior mathematically, linking acceleration to distance from the Sun and to assumed volatile species. These models are applied next, not because 3I/Atlas looks like a comet, but because this is the most common cause of such deviations. Parameters are adjusted. Water ice sublimation is tested first since it dominates cometary activity near the inner solar system. The results do not align well. The timing and magnitude of the acceleration do not match the expected profile. Carbon dioxide and carbon monoxide follow with lower sublimation temperatures and different heliocentric dependencies. These fit slightly better, but still imperfectly. The models require finely tuned conditions, gas escaping without dust, in amounts just sufficient to explain the motion while leaving little visible trace. Radiation pressure is considered next. Sunlight carries momentum, and when it strikes an object, that momentum is transferred. For large bodies, the effect is negligible. For very small or very thin ones, it can matter. The equations are straightforward, derived from classical electrodynamics. Astronomers estimate the object's area to mass ratio from brightness and assumed reflectivity. If the ratio is high, radiation pressure could contribute meaningfully to acceleration. Here the uncertainties widen. Brightness depends on albedo, which depends on surface composition and texture. A dark, compact body and a bright, porous one can reflect similar amounts of light, while responding very differently to radiation pressure. Models explore a range of plausible values. Some combinations can reproduce the observed acceleration, but they imply unusual physical properties, extreme thinness, high porosity, or low density, beyond what is commonly observed in solar system bodies. Thermal forces enter the discussion. As an object heats unevenly, it can re-radiate energy asymmetrically, producing a small thrust known as the Yarkovsky effect. This phenomenon is well documented for asteroids and has measurable consequences over long timescales. Ply to 3 I/Atlas, the effect is calculated and found to be present but insufficient on its own. The directionality does not fully match, and the magnitude falls short. Outgassing models are revisited with more nuance. Instead of uniform activity, localized jets are considered. A small active region on an irregularly shaped body could produce acceleration without a global coma. Rotation complicates the picture further. If the spin axis is oriented just so the net force could align with observations while remaining visually subtle. This scenario is plausible, but it relies on parameters that cannot be independently verified with current data. Each explanation is neither accepted nor rejected outright. Instead, they accumulate qualifiers. Could it be cometary outgassing? Possibly under specific conditions. Could radiation pressure play a role? Yes, if the structure is unusual. Could thermal effects contribute marginally? The models overlap, intersect, and sometimes compensate for one another. None stands alone with decisive clarity. This is where standard practice reveals its strength. Rather than choosing the most intriguing explanation, astronomers compare the minimum complexity required by each. They ask which model demands the fewest assumptions beyond established physics. The goal is not to be right immediately, but to be conservative. Extraordinary claims are postponed not out of fear, but out of discipline. Statistical methods are applied to quantify uncertainty. Monte Carlo simulations explore parameter space varying inputs within plausible ranges to see how often outcomes match observations. Sensitivity analyses identify which assumptions matter most. Often small changes in poorly constrained variables produce large shifts in results. This sensitivity itself becomes a finding. It signals that the system is underdetermined by available data. Independent teams repeat these analyses. Some emphasize dynamical fits, others focus on physical modeling. Their conclusions converge in tone if not in detail. The behavior of 3 I/Atlas can be explained without invoking new physics, but not without stretching existing categories. The explanations work, but only just. They leave little margin. Historical analogues are consulted. Oumuamua, the first known interstellar object, exhibited non-gravitational acceleration without obvious outgassing, prompting similar debates. 2 I/Borisov. The second behaved more like a conventional comet. Together they form a small but instructive sample. 3 I/Atlas appears to sit somewhere between them, sharing traits with both, while matching neither exactly. This comparison tempers interpretation. It suggests that diversity among interstellar objects is real, not anomalous. The solar system may have conditioned expectations that are too narrow. What seems strained here may be common elsewhere. Still, analogy is not explanation. Each object must be understood on its own terms. He notes how the process itself shapes the narrative. In public discourse, uncertainty often reads as failure. In science, it is a signal that inquiry is proceeding correctly. Every model applied to 3i/Atlas leaves a residue of doubt, but that residue is measured, documented, and shared. There is no rush to closure. As time passes, new data arrives incrementally. Additional astrometric points refine the trajectory. Photometric measurements extend the light curve. Each update nudges models slightly, rarely overturning them. The broad picture remains stable. Standard forces can account for the motion, but only with carefully chosen parameters. This cautious conclusion is not disappointing. It is instructive. It shows the reach and the limits of current understanding simultaneously. The physics used to model planets and comets still applies, but the space of possibilities is larger than once assumed. Interstellar objects test the edges of that space. He allows the section to settle on this recognition. Applying standard explanations is not about forcing an object to fit, but about learning where the fit loosens. 3. I/Atlas resists easy categorization, but it does not defy physics. It reveals instead how much flexibility exists within known laws, and how much remains unconstrained by observation. The work continues quietly as it always does. Models are refined papers, revised assumptions re-examined. No single explanation claims victory. The object moves on indifferent to the scrutiny it has inspired. What remains is a clearer sense of process, and a reminder that understanding advances not through dramatic leaps, but through careful elimination, steady comparison, and the patience to remain with uncertainty when certainty is not yet earned. The inward journey now reaches a region where sunlight is no longer a background condition, but a dominant physical presence. The energy arriving at 3i/Atlas increases steadily, not abruptly, yet the cumulative effect is significant. Surface temperatures rise into ranges where material responses are no longer theoretical but expected. This is the zone where models that once remained abstract begin to intersect directly with observation. The object is no longer distant enough for ambiguity to hide entirely in noise. If something changes, instruments are now capable of registering it. Thermal balance becomes central. Every exposed surface absorbs solar radiation and re-emits energy as heat. The equilibrium temperature depends on distance, reflectivity, rotation rate, and surface texture. Analysts compute these values conservatively, assuming simple geometries and average properties. Even under cautious assumptions, the surface warms to levels where volatile substances, if present near the exterior, would respond measurably. Water ice would begin to sublimate slowly. More volatile compounds would do so earlier and more readily. Attention turns again to imaging. High-cadence observations search for diffuse light around the nucleus. A coma, even a faint one, would scatter sunlight and appear as a subtle halo. None is seen. The object remains point-like, indistinguishable from a star except for its motion. This absence is now meaningful. It constrains surface composition and structure more tightly than before. If volatiles exist, they are either deeply buried, depleted by long interstellar exposure, or released in a manner that produces little dust. Dust production is as important as gas release. In typical comets, gas drags dust grains outward, creating visible tails. Gas without dust is harder to detect. Spectroscopic searches are therefore refined. Narrow wavelength bands associated with common molecular emissions are monitored. Sensitivity improves as brightness increases. Results remain consistent with non-detection. Upper limits are placed on production rates. These limits are low but not zero. They leave room for activity below detection thresholds. Meanwhile, astrometric analysis grows more sensitive. With a longer observational arc, small deviations accumulate coherently. What once appeared as marginal residuals now form a pattern. The acceleration remains small, but it is persistent and directional. It does not fluctuate randomly. This persistence is critical. Random noise averages out. Systematic effects do not. The direction of the acceleration is examined relative to the Sun object line. It aligns broadly away from the Sun as many radiation-driven or outgassing forces would. The magnitude is quantified carefully. It is weaker than typical cometary non-gravitational forces at similar distances, but stronger than can be dismissed as numerical artifact. Analysts revisit earlier data confirming that the effect was absent or undetectable at larger distances. This establishes onset. Whatever the cause, it becomes active only after sufficient solar heating. This timing narrows possibilities. Radiation pressure models are recalculated with updated brightness measurements. If the object reflects more light than previously assumed, the force would be stronger. Albedo estimates are revised within plausible bounds. Even at the high-end, radiation pressure alone struggles to fully account for the observed acceleration unless the object's mass is very low relative to its area. Such a configuration is unusual but not forbidden. Porous aggregates loosely bound could behave this way. Interstellar travel might favor their survival as lower density reduces collision damage. Thermal re-radiation effects are also reconsidered. As the object rotates day and night, sides exchange roles. If rotation is slow, heat redistribution is uneven, enhancing anisotropic emission. This could produce a steady thrust. Rotation period estimates remain uncertain, but constraints improve. Photometric variability suggests a period on the order of hours to days, not minutes. This range allows thermal effect but limits their strength. Outgassing models are refined with more realistic assumptions. Instead of uniform surfaces, patchy activity is explored. A small fraction of the surface could host volatile pockets venting gas preferentially. If dust grains are large or cohesive, they may not be easily lifted, suppressing visible coma formation. Gas would escape nearly invisibly, imparting momentum without optical signature. This scenario fits within known physics, though it requires specific conditions. Crucially, none of these explanations violates conservation laws or demands unknown forces. They operate within established frameworks. What challenges scientists is not impossibility but constraint. Each explanation occupies a narrow parameter space. The overlap between acceptable values and observed behavior is limited. This narrowness is what draws attention. Comparisons to earlier interstellar objects intensify. Oumuamua showed a similar pattern acceleration without obvious coma. For that object, radiation pressure and hydrogen outgassing were proposed. Hydrogen is difficult to detect and could escape without dust. Could 3i Atlas share this trait? Models are tested. Hydrogen sublimation requires specific formation histories and surface chemistry. It is plausible, but difficult to confirm. Borisov, by contrast, displayed textbook cometary activity. Its gas and dust were easily observed. The contrast between these objects suggests diversity rather than anomaly. Interstellar space may deliver bodies with a wide range of compositions and structures. The solar system's comets represent only a subset of this diversity. As Section 7 proceeds inward conceptually, attention narrows from environment to surface processes. Microscopic properties now matter. Grain size, porosity, thermal conductivity, and tensile strength influence macroscopic behavior. These properties cannot be measured directly, but they leave signatures in how the object responds to heating. The slow, steady acceleration suggests a stable process, not an explosive one. There are no sudden outbursts, no spikes in brightness. Everything changes gradually. This gradualism reinforces a picture of equilibrium rather than instability. Whatever force acts on the object adjusts smoothly as conditions change. This smoothness argues against structural failure or episodic events. It favors continuous processes like sublimation or radiation-driven effects. The scientific posture remains cautious. Papers describe findings with conditional language. Terms like consistent with and compatible with dominate. Definitive statements are avoided. This is not indecision, but precision. With limited data, overcommitment would be misleading. Public interpretation sometimes races ahead, drawn by phrases that hint at purpose or intent. Within the research community, such language is absent. Motion is described, not interpreted. Acceleration is measured, not attributed motive. The role is observational, not narrative. As the object continues inward, the window for observation narrows. Eventually, geometry and brightness will limit further study. Section 7 ends with this recognition. The object is now in the regime where its interaction with sunlight is undeniable. Something is acting upon it. That action is measurable, repeatable, and constrained. It does not yet demand new explanations, but it presses existing ones to their edges. The groundwork is laid. The environment has done its part. The surface has responded. What remains is to follow the consequences inward into the finer scales where cause and effect must finally meet. With the external environment now fully established, attention moves inward to the forces acting directly on the body itself. The question is no longer whether 3i Atlas responds to sunlight, but how that response is transmitted through its material. At this stage, interpretation depends less on orbital geometry and more on physical structure. The object is treated as a system, not a point. Its behavior reflects the interaction between energy input and internal properties, many of which must be inferred indirectly. The acceleration measured earlier is small but persistent, which implies a force that is steady rather than impulsive. Steady forces require continuity in material response. This immediately disfavors explanations based on sudden fracture, explosive release, or transient instability. Instead, it suggests processes that operate over extended time, maintaining direction and magnitude as conditions evolve. Sublimation, thermal emission, and radiation pressure all fit this general requirement, but each interacts differently with internal structure. Density becomes central. A dense monolithic body responds sluggishly to external forces. A porous or fractured one responds more readily. Brightness measurements provide partial clues. If the object were very dense and compact, its area-to-mass ratio would be low, making radiation-driven effects weak. The observed acceleration implies either a larger effective area or lower mass than such a body would have. This inference is not definitive, but it narrows the range. Porosity is therefore considered carefully. Many small bodies in the solar system are not solid rock, but aggregates of smaller pieces held together weakly. Such structures are known from cometary nuclei and rubble pile asteroids. They have low bulk density and high surface area. Interstellar formation environments could plausibly produce similar or even more extreme structures. Long exposure to radiation and collisions might erode denser components, leaving behind lighter frameworks. Thermal conductivity follows from structure. In a porous body, heat penetrates slowly. The surface warms while the interior remains cold. This gradient can sustain sublimation at shallow depths, while deeper layers remain inert. It can also produce anisotropic thermal emission, as the warm surface radiates more strongly in some directions than others, depending on rotation and shape. These effects are subtle but cumulative. Rotation becomes more relevant here. Even a modest spin can average out localized forces, while slow rotation allows them to persist. Photometric data continues to suggest a rotation period that is neither extremely fast nor extremely slow. This intermediate regime permits directional forces to act without being fully cancelled. Models explore this balance, showing that smaller symmetries can survive over many rotations. Surface heterogeneity is another factor. Real objects are not uniform. They have patches of different composition, texture, and history. A region enriched in volatiles could dominate the force budget, even if it covers a small fraction of the surface. Conversely, a mantle of processed material could suppress activity almost everywhere. The absence of visible dust implies either a cohesive surface layer or gas release mechanisms that do not entrain particles easily. Gas dynamics at low pressure differ from everyday intuition. In near-vacuum gas, molecules escaping a surface do not collide frequently. They stream outward, transferring momentum directly. If the surface pores are narrow, gas can escape directionally, enhancing thrust. This is well understood in laboratory studies and applied physics. It does not require extraordinary conditions, only specific microstructures. The persistence of acceleration suggests that whatever structure exists is stable under increasing heat. It does not collapse or seal itself as activity proceeds. This stability argues against loosely bound frost layers that will be lost quickly. It favors materials that have been processed and compacted over time, perhaps during interstellar travel. Cosmic rays and micrometeoroid impacts can sinter surfaces, increasing strength while retaining porosity beneath. Radiation pressure is revisited with this internal perspective. For radiation pressure to matter significantly, the object must present a large effective cross-section relative to its mass. This could be achieved not only by thinness, but by fluffiness. A highly porous aggregate scatters light efficiently while containing little mass. Such aggregates are fragile in planetary systems, but interstellar space is comparatively empty. Survival there is plausible. These considerations do not point to a single model. Instead, they outline a family of possibilities. Each member of this family satisfies known physics and matches observations within uncertainty. The difficulty lies in distinguishing among them with available data. Remote sensing provides integrated signals, not detailed maps. Multiple internal configurations can produce similar external behavior. The scientific response is to map this degeneracy explicitly. Researchers publish ranges rather than values. They describe envelopes of possibility. This approach is conservative, but it preserves accuracy. It also resists narrative temptation. The object's behavior may look coordinated, but coordination is not inferred. Forces act without intent. Structure channels them without purpose. Language is chosen carefully. Terms like active as inert are used descriptively, not metaphorically. Activity refers to measurable processes, not agency. This distinction is maintained rigorously in technical discourse, even when popular summaries blur it. Within the analysis, 3i Atlas remains an object responding mechanically to its environment. As the object moves further inward, its time under intense solar influence lengthens. If internal volatiles exist, depletion should begin to show effects. Acceleration might weaken as sources exhaust. Alternatively, it could strengthen if deeper layers are exposed. Monitoring continues. Early indications suggest relative stability. The force does not drop abruptly. This suggests either a substantial reservoir or a process not limited by volatile supply. Hydrogen outgassing remains a candidate. Hydrogen can be trapped in amorphous ice and released gradually upon heating. It is nearly invisible observationally and does not carry dust. Its molecular weight is low, making it efficient at producing thrust per unit mass lost. Models incorporating hydrogen can reproduce observed acceleration with modest assumptions. However, confirming its presence remotely is extremely challenging. Another possibility is that multiple small effects combine. Radiation pressure, thermal emission, and minor outgassing could each contribute a fraction of the total acceleration. Together, they could match observations without any single process dominating. This composite explanation is less elegant, but often nature prefers complexity. It also reduces the need for extreme parameter values in any one model. Throughout this inward turn, restraint remains the guiding principle. The object does not require reinterpretation of physics. It requires careful accounting of how physics operates under conditions rarely sampled before. Interstellar objects provide such conditions by default. They arrive pre-processed by environments unlike those near the Sun. Section 8 settles on this inward view. The focus is no longer on what the object does, but on what it is. That question cannot be answered definitively, but it can be bounded. The bounds are informed by observation, constrained by theory, and widened by humility. The object continues on its path, carrying its internal structure with it, unchanged by speculation and unaffected by the attention it receives. The work now is to follow that structure further inward toward the smallest scales, where material properties finally dictate response. The inquiry now narrows further, moving from bulk structure toward the smallest scales that still influence motion. At this level, 3i Atlas is no longer considered primarily as a shape or a mass, but as a collection of materials interacting with energy, particle by particle. The observed acceleration, already constrained at larger scales, must ultimately arise from countless microscopic exchanges of momentum. Understanding these exchanges does not require new physics, but it does require attention to regimes that are rarely observed directly. At the surface, sunlight arrives as a stream of photons. Each photon carries momentum, and when it is absorbed or reflected, that momentum is transferred. For a smooth, reflective surface, the effect is straightforward. For a rough, porous one, the interaction becomes complex. Photons penetrate cavities, scatter multiple times, and deposit energy unevenly. This uneven deposition translates into uneven heating. Even slight asymmetries can produce net forces when integrated over time. Thermal emission follows absorption. Heated material emits infrared radiation in all directions, but not necessarily uniformly. The direction and intensity depend on temperature gradients, which depend on conductivity and geometry. In porous materials, heat does not flow freely. Grains touch at limited contact points. Voids interrupt conduction. As a result, some regions remain warmer, longer, radiating more strongly in preferred directions as the object rotates. The recoil from this radiation is small per unit area but persistent. Laboratory studies of analogous materials inform these models. Experiments on regolith simulants show that porosity can amplify thermal effects beyond simple predictions. When applied to 3I Atlas, these findings suggest that thermal recoil could contribute meaningfully, especially if combined with other forces. The key is persistence. Thermal emission operates continuously as long as sunlight is present. Gas release, if it occurs, operates at the same microscopic scale. Molecules trapped in pores gain energy and escape when thermal conditions permit. Each escaping molecule imparts momentum equal to its mass times velocity. For light molecules, velocity is high. Hydrogen in particular escapes rapidly. Even a small flux can produce a measurable force over time. Because these molecules interact weakly with dust, their escape can be nearly invisible. The microstructure of the surface controls this process. Narrow pores collimate gas flow. Wide cavities disperse it. If the distribution of pore sizes is uneven, gas release becomes directional. Directionality is essential for producing net acceleration. Without it, forces cancel. This requirement places constraints on surface morphology, but it does not eliminate plausibility. Natural processes can produce anisotropy without design. Radiation damage accumulated over interstellar travel may shape this morphology. High-energy particles break chemical bonds, alter crystal structures, and gradually change mechanical properties. Over millions of years, surfaces evolve. Volatile rich layers may retreat inward. Refractory residues may accumulate. This stratification affects how energy is absorbed and released when the object enters a stellar system. The absence of dramatic change as 3I Atlas approaches the Sun suggests that its surface has already reached a stable configuration. There is no sudden exposure of fresh material. Instead, responses scale smoothly with input energy. This smooth scaling aligns with a processed surface that has lost its most reactive components long ago. At this scale, even dust grains matter. Grain size influences optical properties. Fine grains scatter light efficiently and heat quickly. Larger grains absorb more slowly and retain heat longer. A mixture of sizes produces complex behavior. Observations of brightness and color provide indirect clues. The relatively neutral spectral slope suggests grains that have been altered but not dominated by extreme compositions. Electrostatic effects are also considered. Sunlight can charge surfaces through photoelectric emission. Charged grains can experience forces in the solar wind. However, calculations show that for objects of this size and distance, such effects are negligible compared to radiation and thermal forces. They are acknowledged and set aside. Statistical mechanics underpins all of these considerations. The macroscopic force is the sum of microscopic events. No single photon or molecule matters, but the ensemble does. The challenge lies in estimating ensemble behavior without direct measurement. Models rely on assumed distributions informed by analogous systems. These assumptions are tested by their consequences. If predicted acceleration matches observation under reasonable parameters, the model remains viable. This inward focus also clarifies why interpretation must remain restrained. At microscales, many different configurations can yield similar macroscopic outcomes. Degeneracy is high. Without direct sampling, certainty is unattainable. The goal is therefore not identification but exclusion. Scenarios that violate energy balance, momentum conservation, or observed stability are removed. What remains is a constrained set of possibilities. He notes that none of these processes implies coordination or intent. They operate automatically, governed by local conditions. The language of appearance often used informally does not apply here. Forces act, materials respond, motion results. The sequence is sufficient. As the object continues inward, monitoring focuses on whether microscale processes evolve. A decline in acceleration would suggest depletion of volatile sources. An increase could indicate deeper layers becoming active. So far, changes are modest. The force remains within a narrow range. This steadiness implies either a large reservoir or a process dominated by radiation rather than mass loss. Hydrogen remains difficult to assess. Its escape would not significantly alter brightness or produce dust. Its detection requires indirect inference. Some models predict subtle changes in acceleration profile that could be diagnostic. Analysts watch for these patterns. Data quality improves, but geometry also shifts, complicating interpretation. There is no decisive signal. The inward progression of analysis mirrors the inward motion of the object itself. From orbit to environment, from structure to surface, from surface to grain, each layer constrains the next. By the end of this section, the problem is well framed. The remaining uncertainty is not due to ignorance of physics, but to limits of observation. Section 9 concludes with this refined view. 3. iAtlas behaves in a way that is fully consistent with known microphysical processes acting under uncommon conditions. Its acceleration emerges naturally from interactions that are individually simple, but collectively subtle. The appearance of deliberateness dissolves at this scale, replaced by a tapestry of energy exchange that requires no guide in hand. What remains to be examined lies even deeper in the statistical patterns that emerge over time as these processes continue. Attention now shifts from instantaneous mechanisms to accumulated behavior over time. At this depth of analysis, the object is understood not just through forces acting at a given moment, but through how those forces integrate across its passage through the inner solar system. Motion is no longer a snapshot, it is a record. Each small acceleration contributes to a trajectory that slowly departs from what gravity alone would produce. The task here is to read that record without projecting meaning onto it. Time series analysis becomes central. Observations are ordered chronologically and deviations are tracked as functions of heliocentric distance, solar phase angle, and elapsed exposure to sunlight. Patterns are sought not in isolated data points, but in their continuity. The acceleration does not spike. It does not oscillate erratically. Instead, it follows a smooth curve that rises as solar input increases and then stabilizes within a narrow range. This behavior immediately rules out transient events as dominant causes. Impacts, fractures, or episodic eruptions would leave sharp signatures. None are present. The stability of the signal suggests a quasi-steady state. Whatever process drives the acceleration adjusts gradually as conditions change. This adjustment implies feedback. As heating increases, response increases, but not without limit. At some point, additional energy does not produce proportionally greater force. This saturation can arise in several ways. Volatile release may become diffusion limited. Thermal gradients may equilibrate more efficiently. Radiation-driven effects may approach geometric constraints. Each possibility is examined. Mathematical fits are applied to the acceleration curve. Simple power laws, exponential responses, and physically motivated sublimation models are compared. No single functional form stands out dramatically. Several fit within uncertainty. This multiplicity reinforces earlier conclusions about degeneracy. The data does not select a unique mechanism. It constrains families of behavior. Residual analysis is also performed. After subtracting best fit models, remaining deviations are inspected. They show no clear periodicity. This absence suggests that rotation does not strongly modulate the net force, or that modulation averages out over the sampling interval. This result aligns with a body whose active regions are either distributed or whose rotation axis orientation reduces observable variation. Longitudinal stability is particularly informative. Over weeks and then months, the direction of the acceleration remains aligned roughly away from the Sun. It does not drift significantly. This alignment is expected for forces tied directly to solar input. It would be difficult to maintain otherwise without invoking mechanisms unsupported by evidence. The Sun remains the only plausible energy source. Comparative analysis with synthetic populations provides context. Simulated interstellar objects with varying properties are passed through virtual solar systems. Their responses to solar heating are computed. Some match observed behavior, others do not. Those that do often share traits already inferred: low density, moderate porosity, limited dust production, and stable structure. This convergence, while indirect, increases confidence that the explanation lies within known physical regimes. Historical data is also revisited. Earlier observations, once too noisy to interpret, are reanalyzed using updated models. Subtle trends emerge. The acceleration likely begins gradually at distances slightly farther out than originally detected. It was present, but buried in uncertainty. This finding smooths the narrative further. There is no sudden onset, only gradual emergence as sensitivity improves. The object's passage through this region of space is finite. Observers are aware that opportunities diminish as geometry changes. This awareness shapes priorities. Resources are allocated to maximize temporal coverage rather than chase speculative signatures. The goal is to complete the record as fully as possible, not to resolve every ambiguity. Throughout this process, terminology is guarded. Words implying intention are avoided in technical contexts. Motion is described as responsive, not purposeful. When public communication requires metaphor, it is carefully bounded. Internally, the discipline remains strict. The object is not doing anything in a cognitive sense. It is undergoing. This distinction matters because time-integrated behavior can tempt interpretation. A steady acceleration in a consistent direction can look deliberate. But at this scale, deliberateness dissolves into causality. The force does not anticipate future positions. It responds to present conditions. The apparent coherence arises from the stability of those conditions, not from planning. Models exploring depletion effects are monitored. If the acceleration begins to decline as the object moves inward, it would suggest limited reservoirs. If it increases, deeper layers may be engaging. If it remains constant, radiation-driven effects may dominate. At this stage, evidence points to modest variation, not dramatic change. This steadiness further constrains models favoring those with self-regulating responses. The analysis also considers what is not seen. There is no sudden brightening, no fragmentation, no tail emergence. These absences are as informative as detections. They indicate structural integrity. The object withstands increasing thermal stress without failure. This resilience implies cohesive strength above minimal rubble piles but below monolithic rock. It suggests a balance achieved through long processing. Interstellar travel itself becomes relevant again, not as speculation but as conditioning. An object exposed to cosmic environments for millions of years experiences slow but relentless modification. Weak components are removed. Stable configurations persist. By the time such an object encounters a star, it may already represent a filtered outcome. What is observed is not a random sample of formation, but a survivor. Time integration also clarifies scale. The total change in velocity imparted by the non-gravitational acceleration is small compared to the object's overall speed. It does not dramatically alter its fate. It will not be captured. It will not spiral inward. The acceleration matters scientifically, not dynamically. This perspective tempers interpretation. The effect is real but modest. As Section 10 concludes, the object's behavior over time appears coherent, constrained and physically grounded. The record shows no surprises, only refinement. Each additional day of data tightens bounds without overturning understanding. The object continues on its path, and the accumulated evidence supports a picture of steady interaction rather than anomaly. What remains is not to explain more, but to recognize limits. Time integration has extracted as much signal as possible from available observation. Further insight would require different kinds of data. The analysis pauses here not because curiosity is satisfied, but because the object has revealed all it can at this scale. The inward journey of understanding must continue, but it will now move toward interpretation boundaries rather than new measurements. At this stage, analysis approaches the boundary where description ends and interpretation begins. The data gathered so far has been examined through physical models, time integration, and microscale processes. What remains is not a new mechanism, but the way patterns are perceived and framed. Section 11 therefore turns inward again from forces and materials to inference itself. The object has not changed. The lens through which it is viewed now becomes the subject of scrutiny. Human pattern recognition is powerful and automatic. When motion appears coherent over time, it invites explanation beyond mechanics. A trajectory that adjusts smoothly can resemble guidance. This resemblance is superficial, but it is persistent. Scientific method exists in part to counter this instinct, replacing impression with quantified uncertainty. Here that replacement is explicit. The appearance of coordination is examined as an artifact of steady processes operating under stable conditions. Statistical framing plays a central role. The acceleration of 3i Atlas is real within measured uncertainty, but its signal-to-noise ratio remains modest. Small forces integrated over time can look intentional when plotted, especially when data gaps are filled by interpolation. Analysts therefore test alternative visualizations. When acceleration vectors are shown with uncertainty, envelopes rather than single lines, the impression softens. The motion remains consistent but not precise in the way guided systems are. Bayesian methods are applied to formalize this restraint. Prior probabilities favor ordinary physical explanations because they have explanatory history. Likelihood functions incorporate observational error and model uncertainty. Posterior distributions show that while some explanations are more probable than others, none dominate overwhelmingly. This distributional view resists narrative collapse. It keeps multiple possibilities active without privileging one prematurely. Language is adjusted accordingly. Technical papers avoid verbs that imply agency. Phrases are chosen to describe response rather than action. Acceleration is attributed to forces, not decisions. Even metaphors are minimized. Where metaphor is unavoidable, it is flagged as such. This care reflects awareness that interpretation can outrun evidence quickly, especially when dealing with rare phenomena. The rarity of interstellar objects amplifies this effect. With only a few examples, baseline expectations are weak. Any deviation from solar system norms can feel significant. Section 11 emphasizes that rarity does not imply exceptionality in physical law. It implies limited sampling. The sample size is too small to define typical behavior, let alone outliers. What appears unusual may simply be underrepresented. Comparative frameworks are therefore stressed. Instead of asking whether 3i Atlas behaves strangely, analysts ask whether its behavior falls within the envelope of plausible outcomes for bodies formed and processed outside the solar system. This reframing shifts emphasis from anomaly to diversity. Diversity accommodates variation without invoking novelty. Simulation studies support this shift. Large ensembles of hypothetical interstellar objects are modelled with random but physically plausible properties. When passed through stellar environments, a subset exhibits behaviour similar to that observed. These subsets are not rare within the simulated population. They are rare only in observation because detection itself is difficult. This distinction matters. Observational rarity does not equate to physical improbability. Section 11 also addresses the role of thresholds. Detection thresholds create apparent discontinuities. When an effect crosses from undetectable to detectable, it can seem sudden even if it has been present all along. The acceleration of 3i Atlas likely existed earlier at lower magnitude. Its recognition coincides with instrument sensitivity, not with onset. This understanding dissolves some of the perceived abruptness. Attention turns to how intent is defined. Intent implies internal representation, goal orientation, and adaptive response based on future states. None of these are evidenced. The object does not change behavior in anticipation of conditions. It responds locally and contemporaneously. The consistency of response arises from stable input, not from planning. Section 11 makes this distinction precise, not philosophical. Historical parallels are instructive. In earlier centuries, cometary motion was once interpreted as purposeful or ominous because it defied circular planetary paths. As understanding improved, the mystery receded. The comets did not change, the framework did. Section 11 places 3i Atlas within this lineage. It is not unique in provoking interpretive tension, it is current. The discipline of astronomy has learned to separate explanation from implication. Explaining acceleration does not require explaining why in a teleological sense. It requires explaining how. That task has largely been accomplished within uncertainty bounds. What remains unresolved lies in parameter estimation, not in principle. Public discourse is acknowledged indirectly. Outside technical context, language often compresses nuance. Headlines prefer clarity. Words like intent appear because they attract attention. Section 11 does not engage this directly, but it recognizes the gradient between careful analysis and popular summary. The internal record remains insulated from that gradient. The object's continued motion provides a grounding counterpoint. It follows its trajectory indifferent to interpretation. Its path is not altered by language. This indifference reinforces methodological humility. Understanding is provisional and asymptotic. It approaches truth without claiming possession. As analysis moves inward, still attention turns to epistemic limits. Remote observation constrains inference fundamentally. Without direct sampling, certain questions remain unanswerable. Composition can be inferred but not confirmed. Structure can be modelled but not imaged. This limitation is not a failure. It defines the boundary of the current inquiry. Section 11 therefore settles into a reflective but restrained posture. It does not resolve uncertainty by declaration. It contains uncertainty by framing. The appearance of intent is treated as a perceptual artifact arising from coherent response to consistent forces. The data supports this interpretation sufficiently to exclude more elaborate ones without exhausting possibility. In closing this section, the focus narrows once more. What remains to be addressed lies not in motion or material, but in how conclusions are communicated and fixed. The inward journey now approaches its innermost layer, where the distinction between observation and narrative must be maintained deliberately. The object continues onward, and the analysis prepares to follow, not with new measurements, but with final constraint. The inward movement now reaches the collective layer where individual measurements and models are absorbed into institutional process. At this level, the object is no longer encountered only by instruments and equations, but by systems designed to regulate interpretation. Observatories, journals, committees, and informal networks of review come into focus. Their role is not to accelerate understanding, but to stabilize it. With 3i Atlas, this stabilizing function becomes especially visible. Data flows first through routine channels. Observations are logged, calibrated, and released according to established schedules. There is no urgency embedded in the object itself, but attention increases because the behavior touches known thresholds of interest. Even so, procedures remain unchanged. Requests for additional observing time are evaluated alongside others. Proposals justify themselves in standard terms, signal value feasibility contribution to broader knowledge. The object does not receive exception by novelty alone. Peer review forms the next layer. Analyses are written conservatively framed around uncertainty and bounded claims. Reviewers examine not only results but tone. Overstatement is flagged, ambiguous phrasing is clarified. Suggestions push authors to separate what is measured from what is inferred. This process is slow by design. It allows excitement to dissipate before conclusions harden. Within institutions, internal discussions occur quietly. Working groups compare notes. Discrepancies between models are explored collaboratively rather than competitively. This culture has been shaped by past experience, where early claims sometimes required later revision. The memory of those revisions informs present restraint. 3i Atlas benefits from that memory even as it tests it. Press communication is treated as a distinct domain. Statements prepared for public release emphasize context. Comparisons to earlier interstellar objects are included to normalize the event. Language is chosen to avoid implication beyond evidence. When words like unusual appear, they are paired with explanations of sampling limits and detection bias. This pairing is deliberate. It is meant to reduce misinterpretation rather than prevent interest. The institutional response also includes what is not done. No special task force is convened. No extraordinary review pathway is invoked. The object does not trigger redefinition of categories. It is processed as an interstellar object, exhibiting non-gravitational acceleration, nothing more. This normalizing response is itself a statement about confidence in existing frameworks. At the same time, caution does not mean dismissal. Resources are allocated carefully. Observations continue while conditions permit. Archival data from other surveys is re-examined to search for prior detections. This backward look sometimes yields additional constraints. In this case, it extends the observational arc, slightly improving fits without altering conclusions. The result reinforces continuity rather than surprise. International coordination is visible but understated. Data is shared across borders routinely. Different facilities contribute complementary measurements. No single institution dominates interpretation. This distributed approach reduces the influence of local bias. It also slows convergence, but that slowness is valued. It allows multiple lines of reasoning to mature independently before comparison. Funding considerations operate in the background. Proposals that reference 3i Atlas are evaluated on methodological merit rather than speculative payoff. This reflects an institutional preference for incremental knowledge over dramatic claims. The object becomes a case study, not a justification. Its value lies in what it reveals about interstellar populations, generally not in any singular narrative. Educational contexts respond as well. Graduate seminars discuss the object as an example of modelling under uncertainty. It is used to illustrate how multiple mechanisms can coexist within error bounds. This pedagogical use reinforces norms. Students learn not just facts, but posture. They learn how to remain with uncertainty without filling it prematurely. Throughout these layers, a common theme persists. The institutions involved are designed to absorb novelty without distortion. They do not eliminate uncertainty, but they prevent it from becoming conflated with speculation. This function is often invisible from outside, but it is critical. Without it, rare objects would repeatedly trigger cycles of overinterpretation. Historical awareness continues to shape behavior. Previous cases where limited data encourage broad claims serve as reference points. In those cases, later observations narrowed interpretation significantly. The lesson drawn is not that speculation is forbidden, but that it must be clearly labelled and structurally separated from evidence. With 3i Atlas, this separation is maintained. Internal debates do occur. Some researchers favour one mechanism over others. Others emphasise composite explanations. These debates are recorded in footnotes and appendices, not headlines. Over time, as citations accumulate, a consensus tone emerges. It is not unanimous agreement, but a shared boundary of acceptable claims. That boundary defines the institutional position. The object's continued motion eventually reduces observational opportunities. As it fades, institutional attention shifts. Papers move from active review to archival reference. The object joins a small but growing list of interstellar visitors. Its role becomes comparative rather than immediate. This transition is smooth. There's no abrupt end to interest, only redistribution. Section 12 recognizes that this process is itself part of the scientific environment. Just as sunlight and gravity act on the object, institutional norms act on interpretation. They shape what is said when it is said, and how strongly it is stated. These norms are not external to science, they are integral to it. By the end of this section, the inward journey has reached a point where remaining questions are less about physics than about limits of inference and communication. Institutions have done what they are designed to do. They have constrained narrative, preserved uncertainty, and integrated a rare observation into a stable framework. The object continues onward, and the system that observed it returns gradually to baseline, carrying forward a refined understanding without disruption. He does not arrive with spectacle. There is no flash, no sudden flare, no announcement written in light. The object known as 3i/Atlas continues its passage in silence, moving through the outer regions where sunlight weakens and assumptions grow thin. Its path remains steady, its acceleration subtle but persistent, a small deviation measured in fractions of millimeters per second squared. To the casual eye, this is nothing. To astronomers, it is the kind of nothing that changes everything. In the long history of astronomy, revolutions rarely begin with explosions. They begin with residuals, with equations that refuse to balance with motion that will not quite behave. 3i/Atlas belongs to that lineage. Its consequences are not dramatic in the moment. They unfold slowly, reshaping the way observation itself is understood. He is measured again and again. Optical telescopes trace reflected sunlight, infrared instruments search for warmth radio arrays, listen for emissions that never come. Each data set agrees on the fundamentals: the object is small, likely a few hundred meters across. Its surface reflects little light. Its trajectory is hyperbolic, unbound to the sun. Yet layered on top of this agreement is a tension. The motion cannot be explained by gravity alone. Non-gravitational acceleration is present, but without the usual signatures. No tail stretches behind it. No coma blooms around it. No gas species announce themselves in spectral lines. The silence is complete. This absence forces a shift. Instead of asking what 3I/Atlas is doing, astronomers begin asking what their models assume without question. He exposes the fragility of categories. For decades, interstellar visitors were expected to behave like comets, because comets were the only small bodies known to accelerate without engines. When the first interstellar object was discovered, its unexpected behavior was treated as an anomaly. The second reinforced the discomfort. By the time 3I/Atlas enters the record, the pattern is no longer ignorable. 3 objects, each different, each unbound to the sun, each defying a neat classification. The consequence is subtle but profound, the realization that the solar system's visitors may represent a far wider diversity than previously imagined. Other planetary systems may produce bodies unlike anything formed here, shaped by different temperatures, different chemistries, different histories of radiation and collision. He changes how absence is interpreted. In astronomy, detection often depends on presence-light heat emission. 3I/Atlas offers almost none of these. Its darkness is not merely a lack of data, it is data. A surface that reflects little suggests processing by cosmic rays over immense timescales, or a composition rich in complex carbon compounds. The lack of outgassing suggests volatiles either buried deeply or absent entirely. These possibilities carry consequences for models of planet formation beyond the Sun. If some systems eject bodies that are devolatilized early, then interstellar space may be filled with objects that are effectively inert drifting relics rather than active wanderers. The sky in that case is not empty but quiet, populated by travellers that rarely announce themselves. He alters the role of surveys. 3I/Atlas is not found because it is bright or dramatic. It is found because modern surveys watch everything all the time. Automated telescopes scan the sky repeatedly, comparing images flagging motion that does not belong. This object is a success of persistence rather than precision. The consequence is a renewed appreciation for scale. Individual instruments matter less than networks. No single telescope solves the mystery. Instead, data accumulates across continents, across wavelengths, across months. Astronomy becomes less about isolated discovery and more about sustained attention. In this way, 3I/Atlas quietly rewards patience, reminding observers that the universe often reveals itself only to those willing to watch without expectation. He also reshapes the conversation around certainty. Early interpretations are cautious, deliberately restrained. No claims of artificial origin withstand scrutiny. No exotic explanations survive contact with data. What remains is uncertainty carefully bounded. This is not a failure of science, but its strength. The response to 3I/Atlas demonstrates a maturity in the field, a willingness to sit with unanswered questions without filling them prematurely. The consequence is cultural as much as technical. Astronomers become more comfortable saying we do not yet know, and in doing so they preserve the integrity of what is known. He introduces new priorities. Future missions are discussed not in terms of spectacle but interception. If objects like 3I/Atlas are common, then the ability to reach one quickly becomes valuable. Concepts emerge: rapid response probes, modular spacecraft waiting in parking orbits, instruments designed for flybys measured in hours rather than years. These ideas remain theoretical, but their origin can be traced to moments like this when an object passes through and cannot be touched. The consequence is a shift in imagination, from static exploration to responsive exploration, from planned destinations to opportunistic encounters. He reframes interstellar space itself. Once considered a near vacuum punctuated by stars, it now appears as a medium carrying debris memories of distant systems. Each interstellar object is a sample not of one place, but of processes repeated across the galaxy. 3. I/Atlas becomes a messenger without a message, a fragment whose mere existence conveys information. It tells of collisions in other systems, of gravitational scattering, of the efficiency with which planets eject material into the void. The consequence is a more dynamic picture of the Milky Way, not as a static collection of stars, but as a churning environment where material is constantly exchanged. He affects education and public understanding in quieter ways. Unlike dramatic images of nebulae or galaxies, 3I/Atlas offers no obvious visual reward. Its story must be told through motion, through graphs and residuals and careful language. This demands a different kind of engagement, one that values process over imagery. For those who listen, it becomes an introduction to how science actually works, slowly, collaboratively, often without resolution. The consequence is subtle trust. An audience that understands why answers take time is more likely to accept uncertainty as honest rather than evasive. He leaves behind a legacy before he leaves the solar system. Long after 3I/Atlas fades beyond detection, its data remains. Papers will cite it. Models will incorporate it. Lectures will reference it as an example of measured restraint. It will not become famous for what it was, but for what it did to the field. It forces refinement. It forces humility. It forces the acknowledgement that even now, with telescopes of extraordinary power, the universe retains the ability to surprise in the smallest ways. He moves on unaltered by the attention. The sun's gravity weakens the object's path, straightens, and eventually it rejoins the interstellar dark. There is no farewell. Yet the consequences linger. Assumptions adjusted, questions reframe, priorities reconsidered. In the end, 3I/Atlas does not demand belief or awe. It asks only that observers notice what does not fit and resist the urge to smooth it away. In that restraint lies the quiet power of discovery, and in that power, the reason this small, silent traveller cannot be ignored. He remains attentive long after the calculations are complete. Section by section, the sky continues its slow rotation, and instruments return to their quiet routines. 3I/Atlas is already receding its signal, weakening its measurements, settling into archival stability. Yet its presence lingers not as an object but as a condition. The condition is expectation without prediction. For the first time, astronomers are not merely open to the idea of another interstellar visitor. They are preparing for it. This readiness marks a change deeper than any single discovery. It signals a shift from surprise to anticipation, from isolated anomalies to an emerging population that may in time define a new field of study. He considers the sky differently now. Where once the vastness between stars was treated as emptiness, it is increasingly understood as a corridor. Planetary systems do not keep their material neatly contained. Gravitational interactions scatter debris outward, especially during early formation. Giant planets migrate, destabilize orbits, eject fragments. Over billions of years, this process repeats across the galaxy, filling interstellar space with travelers that carry no destination. The realization is not sudden but cumulative. 3I/Atlas adds weight to it. The consequence is a subtle recalibration of probability. The question shifts from whether such objects exist to how often they pass through unnoticed. He watches the surveys evolve in response. Detection algorithms are refined, trained not only to find bright comets or near-Earth asteroids, but to recognize faint, fast-moving intruders with unusual trajectories. The emphasis moves toward early detection because time matters. An interstellar object is visible for only a brief window, and its scientific value increases exponentially with preparation. The sky is no longer scanned only for threats or spectacle, but for opportunity. Each new dataset is examined with the memory of 3I/Atlas in mind, its quiet acceleration serving as a benchmark for what subtlety can look like. He observes the role of uncertainty expand rather than shrink. With more interstellar candidates expected, not fewer ambiguity becomes a permanent companion. Some objects will be poorly constrained, others lost quickly, their paths reconstructed only approximately. This does not weaken the science. It strengthens its statistical foundation. Patterns emerge not from certainty, but from repetition. If multiple objects show non-gravitational acceleration without visible outgassing, the explanation must account for all of them. If surface darkness appears common, then cosmic processing becomes a central narrative. Waiting in this context is not passive. It is an active accumulation of context. He turns to theory, which begins to stretch in response. Models of small body physics are revisited, especially those involving thermal effects. Radiation pressure, once dismissed for objects of this size, is reconsidered under different assumptions of shape and density. The possibility of porous structures, fractal aggregates, or unusual material compositions gains cautious attention. None of these ideas are declared definitive. Instead, they are held lightly tested against data refined or discarded as needed. The waiting is disciplined. It does not chase novelty for its own sake. It seeks coherence across observations that may arrive years apart. He notices how language adapts. The term interstellar object shifts from a singular curiosity to a category. Subcategories are proposed, debated, refined. Some may resemble comets, others asteroids, others neither. Taxonomy, once stable, becomes provisional again. This is not confusion but growth. Classification follows understanding, not the other way around. 3. I/Atlas, in this sense, functions as a hinge moment, after which the vocabulary of small bodies can no longer be purely solar-centric. The galaxy asserts itself as a source of diversity that demands its own descriptive frameworks. He reflects on the human element of waiting. Astronomers plan careers around timescales longer than any single observation. The anticipation of the next interstellar visitor becomes part of that rhythm. Graduate students design theses that assume such objects will appear. Instrument proposals reference them explicitly. The field normalizes patience, recognizing that discovery is often a matter of being ready rather than being lucky. The sky does not respond to urgency, it responds to continuity. He also recognizes the limits of preparation. Even with advanced surveys and rapid response concepts, most interstellar objects will pass through beyond reach. They will be detected, late observed briefly, and then gone. This impermanence is not a flaw. It is the nature of the phenomenon. Waiting, therefore, includes acceptance. The acceptance that some data will always be incomplete, that some questions will remain partially answered. The consequence is a science comfortable with gradients rather than absolutes. He contemplates the broader implication for planetary science. If interstellar objects are common, then the solar system is not unique in ejecting material. It participates in a galactic exchange that blurs the boundaries between systems. This exchange is slow, diffuse, and indifferent to observers, yet it connects distant regions in ways that challenge the intuition of isolation. 3. I/Atlas is not from here, but it is not entirely alien either. It is shaped by physics shared across the galaxy. The waiting then is also a form of listening for familiarity in the unfamiliar. He notices how public narratives are just becoming quieter. Early excitement gives way to measured curiosity. There are no dramatic revelations, no definitive answers. Instead, there is a steady accumulation of insight. This tone aligns with the reality of the work. Waiting becomes part of the story, not a prelude to it. For those who follow closely, this restraint builds credibility. It demonstrates that science does not rush to fill silence, but respects it as part of the signal. He understands that the next interstellar object may not resemble 3I/Atlas at all. It may be brighter or faster or chemically active. It may confirm existing hypotheses or dismantle them. The value of 3I/Atlas lies not in prediction but in preparation. It sharpens the questions so that when the next signal appears, attention will already be tuned. The waiting is not idle. It is structured by memory. He remains oriented toward the sky, not with expectation of surprise, but with readiness for pattern. The Milky Way continues its slow rotation, stars orbiting the center, debris drifting between them. Somewhere another fragment is already on its way, though its arrival may not occur for decades. When it does, it will pass through the same gravitational well traced by the same equations, observed by instruments shaped by earlier encounters. In that continuity lies the quiet power of astronomy, the ability to learn not only from what arrives, but from the intervals between arrivals. He waits, and in that waiting the field steadies itself. 3. I/Atlas fades into distance, but it leaves behind a posture rather than a conclusion. A posture of attention without urgency, curiosity without projection. The sky does not promise answers, it offers motion. To notice that motion, and to take it seriously even when it whispers, is the discipline that endures. He does not close the investigation so much as he allows it to settle. By the time attention reaches this final inward boundary, 3I/Atlas has long passed beyond the practical reach of instruments, its photons thinning into the background, its influence reduced to numbers that no longer change. The object itself continues onward indifferent to the structures built to observe it. What remains is not an answer, but a contour of understanding, a clear outline of where knowledge holds and where it dissolves into uncertainty without distress. This boundary is not a failure of explanation, it is a feature of honest inquiry. He reviews what has been established with care. The trajectory is unequivocally interstellar inbound from a direction inconsistent with long-term solar system residence, carrying a velocity that cannot be explained by planetary scattering alone. The motion is measured precisely enough to rule out common errors. The acceleration, small but persistent, remains real within the limits of observation. These facts stand without embellishment. They do not imply intent design or anomaly beyond physics. They simply exist firm enough to be trusted, modest enough to resist interpretation. He considers what the object does not require. It does not require exotic propulsion, nor hidden mechanisms, nor narratives imported from elsewhere. The observed behavior can be approached with extensions of known processes, radiation pressure, acting on low-density matter thermal forces operating subtly over time structural properties that differ from the compact bodies most familiar to solar system studies. None of these explanations are complete. That incompleteness is acceptable. Science advances by narrowing the field of necessity, not by filling every gap immediately. He reflects on how easily the mind seeks closure. When an object behaves unexpectedly, the urge to resolve the tension can be strong, yet restraint has guided every step of this examination. Each hypothesis has been weighed not by how satisfying it feels, but by how tightly it aligns with data. Where alignment weakens, the hypothesis loosens and is set aside without drama. This discipline is quiet, often invisible to those who look only for conclusions. But it is here at this boundary that the discipline matters most. He recognizes that the most important outcome is methodological rather than descriptive. 3. I/Atlas does not redefine physics. It refines attention. It demonstrates how small discrepancies treated patiently can expand conceptual space without breaking it. The object becomes a reminder that nature does not always conform to the categories built for convenience. Categories must remain adjustable. They are tools, not truths. He situates the event within a longer temporal arc. For most of human history, interstellar space was imagined but unreachable, its contents inferred only indirectly. The detection of objects passing through from that space marks a subtle shift in scale. The solar system is no longer a closed laboratory, it is an intersection. This realization carries no urgency, no immediate application. Its importance unfolds slowly as frameworks adapt and expectations recalibrate. He notes the calm with which the scientific community absorbs this shift. There is no rush to canonize 3I/Atlas as singular or transformative. It is treated as a data point that happens to sit near the edge of current understanding. That position grants it significance without spectacle. Over time, as more objects join the sample, its role may change. It may become typical, or it may remain unusual. Either outcome is informative. He allows attention to widen, once more reversing the inward path. Beyond this object lie others, like it some already past, some yet to arrive, most never to be seen. Their existence does not depend on observation. They cross stellar systems silently shaped by formation histories that differ in detail but not in principle. The physics that governs them is shared universal patient. This universality is comforting. It anchors uncertainty within a stable framework. He acknowledges the emotional undertone that sometimes accompanies such studies even when unspoken. There is a quiet awe in recognizing contact with material formed around other stars. Yet awe does not interfere with rigor here. It coexists with it, subdued, regulated, allowed only insofar as it does not distort judgment. The object is not romanticized, it is respected. He turns finally to the role of ignorance, not ignorance as absence but as boundary. The questions left open by 3I/Atlas are clearly marked. What is the exact internal structure? How common are such bodies? What fraction exhibit non-gravitational acceleration? These questions are not burdens. They are invitations extended without pressure. They will be addressed incrementally, if at all, by future observations. No single object carries the responsibility of resolution. He senses the investigation reaching a natural stillness. There is nothing more to extract without new data. The correct response to this condition is pause. In that pause, the work remains intact, neither abandoned nor overextended. The archive holds the measurements. The models remain accessible. The interpretations are documented with their uncertainties intact. This completeness, defined by honesty rather than finality, is sufficient. He lets the narrative loosen its grip on causality and return to observation. A small body enters, behaves within the range of physics and exits. The universe does not explain itself. It presents patterns sometimes clearly, sometimes faintly. To observe those patterns without imposing meaning prematurely is the discipline refined here. He rests at this boundary where explanation meets acceptance. Beyond it lies speculation, which is neither forbidden nor embraced within this frame. It simply waits elsewhere. Here the role remains clear to describe, to test, to stop when evidence ends. The mind follows suit, releasing the need to conclude. 3. I/Atlas continues outward unchanged by the attention it briefly received. Its passage leaves behind no message, no warning, no promise. It leaves only a trace of motion through a system that noticed it for a moment. That noticing was enough. In the vast continuity of the cosmos, even brief clarity has value. He allows the inquiry to dissolve gently into quiet understanding. The sky remains open, the boundary holds, nothing more is required. The attention eases without effort, settling into the broader quiet that surrounds all observation. Beyond objects and instruments, beyond data and interpretation, there is the steady continuity of space itself. Interstellar matter drifts, stars move in long arcs, and the solar system continues its orbit within the galaxy, unchanged by brief moments of notice. What has been examined no longer demands focus. It rests among countless other facts held lightly available without insistence. The mind remains with what is stable. Gravity continues to shape motion. Light continues to travel outward, thinning but persistent. Material formed far from the system passes through without announcement, following paths set long before any measurement. These processes do not accelerate or pause. They do not respond to curiosity. They unfold at their own pace, indifferent and reliable. Understanding here does not arrive as completion. It arrives as balance. There is clarity where data supports it and openness where limits appear. Neither state disturbs the other. The absence of certainty does not imply absence of order. It simply reflects scale. The universe is larger than explanation, and explanation is careful not to pretend otherwise. As attention loosens, further details fade into pattern. Motion becomes continuity. Uncertainty becomes space rather than gap. The investigative posture softens, no longer seeking, no longer resisting. What remains is the calm recognition that observation has its place, and so does rest. The object that prompted this inquiry is already distant. Its influence has ended. The systems that measured it have returned to routine, and the sky resumes its quiet familiarity. Nothing has closed, and nothing needs to. The boundary between knowing and not knowing holds steady, untroubled. Thought slows, following the same restraint that guided the inquiry. There's no need to carry conclusions forward. The night sky remains vast and patient, offering no answers and requiring none. Awareness drifts with it, unanchored, steady and calm.